Hello, folks. Welcome to today's series. And today we are interested in introduction to Algebra. And our main focus will be on rings and fields. And this is just the introduction because rings and fields is a very large area. Now, let's look at what we expect. Now, we will just start off with rings, and we assume that you should by now know a lot about groups. Then we finish off with the concept of fields. Now, let's start with a brief introduction, a brief recap. Now, we first need to know what a binary operation is. And a binary operation, with a binary operation, we need an operation. So we take an operation to be star. We have a set S. So now we say star is a binary operation. If for all S, Y belong to S, you have that S star Y is in S. Now we say star is associative. If we have that A star B star C is equal to A star B star C, and this should work for all elements from S. Now, identity elements. What do we mean by identity elements? We say E is an identity element if for all elements in S, we have that E star A is equal to A star E and is equal to A, where A is coming from S. Now, the identity element is always unique to a group. Now, the inverse. Now, let S be from S. Now, the inverse of S, denoted as S inverse, is the element of the property that S star S inverse gives you E, and S inverse star S also gives you E. So, where E is the identity element. So, you could see that similarly, the inverse of an element is also unique. So we can find an inverse respect to a particular element. We don't have a general inverse in a set, but we can have a general. There's always a general identity element. So take note. Now, if we have a binary operation that satisfies all the four conditions above, then we said the set S and star forms a group. Now let's begin. Let's start off by rings. So a ring R plus dot, and we read the dot as multiplication, is said um, to be a ring if it follows it satisfies these properties. First, R plus should be an abelian group, which means that plus should be commutative. Now, dot, that's multiplication, should also be associative. Then the distributive law should hold that multiplication is distributive over addition. So dot is distributive over addition, which means that the left distribution law, which says that A dot B plus C should be equal to A dot B plus A dot C should hold, and vice versa. Note that in this case, multiplication need not to be commutative. As we go on, we'll explain why it is so. Now let's discuss homomorphism. So let R and R prime be two rings. Now if phi is a map from R to R prime, then we say phi is a homomorphism if phi preserves the operations. And this one we have two operations, addition and multiplication. So if phi of A plus B is the same as phi of A plus phi of B, and phi of AB is the same as phi of A, phi of B, then we say phi is a homomorphism. And note, if phi is also injective and suggests that it is bijective, then we can say phi is an isomorphism. Now let's try some examples. So there are four examples here, but I'll just work out the first one. And you can try the other ones. And if you have problems, you can always reach me via email. Now we have f of x equal to ax. Now, first you have that f of x is yes. Now we realize that the first axiom is satisfied because f of x plus y is the same as ex ey. So the first axiom is satisfied. However, let's consider the second axiom. Let's take x to be 0 and y to be 1. We have that f of 0 is 1 and f of 1 is e. Now f of 0 times 1, that's f of 0 and it's equal to 1. But take note, f of 0 times f of 1 is e. So it's not the same as f of 0 times f of 1. So we have this inequality. Hence, the second axiom fails. Once one axiom fails, we can say the map is not an homomorphism. We don't need to prove all. We just need to show that one axiom failed. So in a typical question, when answering, you don't need to do the first part. You can just show the second part and show that it's not an homomorphism, a ring homomorphism. Now, let's go to subrings. So we say a set S with addition plus is a subring of if it's a subset and it forms a ring. So a subset that forms a ring is what we call a subring. But now let's look at the criteria, because if you have been asked to show whether something is a subring, you don't have to go through all the axioms of a ring. So what you just need to show is that the set S is a subgroup of R plus, and you also have to show that it is closed under multiplication. But that is also lengthy. So we can simplify as this. We can just show that if you pick two elements from S, S1 minus S2 is in S. Take note that minus S2 is not the typical multiplication, but it's the additive inverse of S2. And you have to show that the product is also in S. Then we can conclude that it is indeed a subring. Now, let's move on to some general concepts. Now, let's R be a ring. What is a commutative ring? So a commutative ring is just when you have that the multiplication now in this case is commutative. And we say R is a ring of unity if it has a multiplicative inverse. That's R. So take note, a ring need not to have a multiplicative inverse. But if it does have a multiplicative inverse, then we say a ring of unity. Now look at another concept, unit. A unit is an element which has its multiplicative inverse in R. So there's a difference between unity and unit. So unity is a whole set because we say a ring with unity is a whole set. But we say a unit is an element in the set. That has its multiplicative inverse. So a ring with unity has 1. It has other elements including the multiplicative identity, that's 1. But a unit is they are the elements that have their multiplicative inverse in the ring. Now division ring or scale field. So scale field or division ring is just a ring. That is a ring with unity, and it also has to be a division ring. And take note, there's an extra condition that every non-zero element is a unit. So for you to define a division ring, you have to know commutative ring and what does it means for a ring to have unity. Then what does it mean to be a unit? So a division ring has unity, and every non-zero element is a unit. Now let's look at when we say division. Let's say in a whole R in the space of real numbers, we say 8 divided by 2 is 4. 4 divided by 2 is 2. What we are trying to say is that then there is an element that I can multiply to 2 to get 1. That's why I can divide. So the inverse, so in effect, 8 divided by 4, then I'm multiplying it by the inverse, multiplicative inverse of 4. So in R, we realize that things have its inverse, so multiplicative inverse. In the same case, when you say division ring, we are looking at things that is invertible. Invertible means that they have elements such that you can multiply by them to get 1. So when you are confused, just look at division ring as normal division. Okay. Now let's now define a field. So a field is just a commutative division ring So if you have a ring that is commutative and it's a division ring, then it's a field. So like earlier, a subfield is just a subset that is also a field. And if you want a criteria, then you have to a criteria. Let's say E is a subset of F. You want a criteria for E, then first E should contain at least two elements, and those two elements is a trivial. They are the trivial element. That is the zero, the additive identity, and the set itself. Secondly, if you pick any two elements, their difference, that is S and Y, then S plus the additive inverse of Y should be in E. Then if I pick SY, then the product of S and Y should also be in E. Now, every non-zero element in E should have an inverse. So if you want to check for criterion for subfield, you just need to show these four axioms. Then you'll be good to go. Now let's look at more things to expand that again. So let's go look at zero divisors. Let's look at this. If I say what are divisors of, let's say 10, you say 1, 2, 5, and 10, right? Because if I multiply 2 by 5, I get 10. If I multiply 1 by 10, I get 10. In the same way, when you say zero divisors, there are two elements that are not zero themselves. But when you multiply them, you get 0. So let's look at it, for example, like 10. 2 times 5, they are not 10, but 2 times 5 is 10. In the same way, zero divisors, they are not 0 themselves. But when if you multiply them, you get 0. So we say when two elements behave that way, we say they are zero divisors. Now, an integral domain is a commutative ring with unity with no zero divisors. It's a commutative ring with no zero divisors. So we can now define a field as a field is an integral domain such that every non-zero element is a unit. Every non-zero element is a unit. Let's try some examples so we can understand the zero divisors and integral domain very well. Now, we have 4 examples, but I'll try 2 of them. Let's start with example 2. Now, Z12 is giving us all elements that all the remainders when divided by 12. That's 0 to 11. But take note, if I took 2 elements, 2 times 6, and I multiply them, I get 12. 3 times 4 gives me 12. That means that 2 and 6 are 0 divisors. Once there are 0 divisors, Z12 cannot be an integral domain because it has 0 divisors. Now let's go to another example. Example 3, Z5. Now Z5 has elements 0, 1, 2, 3, 4. Now clearly you could see that multiplication is commutative in Z5. And now there is no other 2 elements I can multiply to get 0. So it has no 0 divisors. Now I have to show that all elements, 1 or 0 elements are units. Now let's begin with 1. 1 times 1 is 1. That is the multiplicative inverse of 1 is 1. So 1 is a unit. Now 2 times 3 is 6. Modulo 5 is 1. So that the multiplicative inverse of 2 is 3. Now we have that the multiplicative inverse of 4 is also 4 itself. So all the non-zero elements are units. So we can conclude that Z5 is a field. Note that generally Zn is a field when n is prime. So when n is prime, you are guaranteed that Zn is a field. But take note, when given a question like this to show that it's a field, you don't have to do it this way. Unless the elements in a field are very, very small, that you can easily show that they are units. Other than that, you have to go through all the axioms. All the axioms. Now, what have we learned today? The main things we've learned today are rings and field. So, rings are just, there is a set with 2 operation plus and dot, such that R plus and billion group, and R dot is a semi-group that's associative, and multiplication is distribution over addition. Now, a field is a commutative division ring or an integral domain where every non-zero element is a unit. Alright, so on this note, we'll end here, and I encourage every one of you to try more examples so you can increase your understanding. If you have any comments, you can reach me via email. And if you have questions, don't hesitate to reach me. You can always subscribe to my channel. So we meet next time. Thank you.